So this is a short video on how to use the Laplace transform in solving some differential equations and also some other things. So I've got a few commands already here, but let's take a look at the main one is the top. When we're dealing with Laplace transform, we want to include integral transforms in our command. So that's with int trans. And if I change that to a semicolon, you can see what functions are there. So we have things like Fourier, Fourier cosine, Hilbert, inverse Fourier. But the ones we want to take are inverse Laplace and Laplace. So let's just do an example. Here's a function e to the minus 2t cosine 3t. And so we can take the Laplace transform just by saying Laplace, and then the function, and then t for the variable that you're taking the Laplace transform of, and then the s is what variable you want to output. So in this case we're inputting a function of t and we want s to be the output variable, and so there we are. So you can also take the inverse Laplace, and so that's inv Laplace, and so you want to put in the first argument here is your function that you want to invert. And then we always use s for our Laplace transform, so we're changing from s back to t. And so you do see that we get back to where we started. Good. So you can take Laplace and inverse Laplace of expressions, but now let's see what happens if we take the Laplace transform of a differential equation. And so here's the differential equation: y double prime plus 3y prime plus 2y equals t squared. And we'll go ahead and take the Laplace transform of the entire differential equation. And so you see here that we do get things in terms of y of 0 and y prime of 0. And so on the right hand side we have the Laplace transform of t squared. Okay, and so what's nice about this is you can take the equation and then solve for the Laplace transform itself. And so this is the right hand side, and the left hand side would be y of our capital Y of s, and you notice that it's in terms of the initial conditions. Okay, so we could either substitute initial conditions now, or we could go ahead and invert it back. And so this is our full solution then to the differential equation. You might notice some pieces here. Here was our initial differential equation, and so you can see that minus 1 and minus 2 are going to be the two roots. And then on this side we have t squared, so our guess using method of undetermined coefficients would be a polynomial of degree 2. And so down below here you see that this part is a function times e to the minus 2t, or an expression in y of 0 and dy of 0, in e to the minus 2t, and this one's in e to the minus t. So those are those two together take up the homogeneous part of the solution, and then here we have the particular part of the solution. Okay, so we could also, down here is where I show you how to substitute the values in. So to substitute, we use the substitute command, and we're substituting y of 0 equals 0 and y prime of 0 equals 1. So if I substitute those in, I get my expression. Good. Then you could plot it. Just for fun, we'll take a look at it. Yeah, so it's these two terms are going to 0, so that's going to leave us with this parabola. And so that's what you're seeing here, is that 1/2 t squared minus 3 halves t plus 7/4. Okay, so here you could also substitute, we could have also substituted into the function of s as well. So instead of going through and taking inverse Laplace then substitution, you could substitute first. And then what's interesting about this is sometimes you want to be able to check your work, and so Maple will also help you with partial fractions. And so if I want to try to find out what the partial fraction decomposition of this is, the command in Maple is to convert the expression into partial fractions there, parfrac, and then the s is the variable. Okay, so what we should see then are let's see, s squared plus 3s plus 2 factors, and so we have all linear factors. So let's see what the partial fraction gives us. Good, so s cubed, there's going to be an s term with a constant, s squared with a constant and s cubed with a constant. And then the two factors of our polynomial were s plus 2 and s plus 1. Good. And now with this partial fraction decomposition, you can also take the inverse Laplace transform. And so notice here I'm using a percentage sign. The percentage sign is for whatever was last computed. It's kind of dangerous to use a percentage sign, but as long as you go in order, it's fine. So in that case, I'll have this. So let's see. We can also use the Laplace transform for things like the Heaviside function and the Dirac function. So maybe I'll replace this with the Heaviside since we're doing that one next. Heaviside. Good. And so in that case we have this differential equation. We just changed the right hand side. We can take the Laplace transform, and you see that we do get the Laplace of the Heaviside there. And so we can solve that for the right hand side. And then let's, instead of doing the inverse Laplace transform right away, let's go ahead and take a look to see what that is. So we'll substitute some values in. Maybe y of 0 equals 1 and dy of 0 equals 0. We'll substitute that into the previous expression. And now I can't ask this for, if I tried to do the partial fraction decomposition on this directly, MATLAB's going to complain, and it's because it's not a rational function. And the reason it's complaining is this e to the minus s power right there. And so what we could do if we wanted to actually check the partial fractions is we could say we want to take L5, and I'm going to separate this out so that one fraction is going to be s squared plus 3s over the denominator, and then the other one is going to be 1 over the denominator. In fact, let's just go ahead and do that. So 1 divided by, now you can use denominator of L4. Let's see if that works. Yep. And so now I can do the convert L5 par frac S. Good. And so you see the partial fraction decomposition of this piece. Then for the other piece, that was an s squared plus 3 times s, and then divided by the denominator of L4. And now I can convert that as well. Let's see, that's L6 par frac. And now it's easy to see how this is going to, what form this is going to take when you do the inverse Laplace. The 1 over s goes away, the s is cancelled here, and so you're just left with a simple expression. Good. So that's how we can use the Heaviside. In fact, let's go ahead and do it then. We can go ahead and take the inverse Laplace transform now of L4 st, and there's our expression. Now we can plot this expression. Maybe I should have labeled it. Let's see, I'm up to 7, I guess. L7. And now if I plot L7, you'll notice here that this function turns on at time 1. So we'll go ahead and plot time from 0 to 3, say. Good. And so at time 1, a different function. So this initial function down here is the decreasing function that's dying off, and then at time 1 we're taken over by this Heaviside. And so over time, right, this piece is also going to die off. So maybe if we plot it for a little bit longer, let's see, oh, there is a constant. So this is going to a constant function. Does that seem right? That the solution should converge to a constant? Let's go back up to the original differential equation and see what was going on there. Ah, yes. So here we have y double prime plus 3y prime plus 2y equals Heaviside. So what this is this is the constant function 1 after time 1. So this is never shut off. And so yes, indeed, our solution should also converge to a constant. Not 1, but a constant. Okay, actually it's converging to the value 1/2. Good. Alright, so that's using the Heaviside function. And now, later on in the next section, we'll be using the Dirac delta function. So I could also use the Dirac here. And so what this is modeling is like a hammer hit on our mass spring system at time 1. Okay, so what's going to happen if you hit the mass spring with a hammer at time 1? That's going to put it in motion. And so if we had 0 initial conditions, for example, let's go ahead and see if we can solve that with 0 initial conditions. Right, really nothing's going to happen until time 1. And so let's go ahead and invert that transform. So in Laplace of L4 st, and it should be 0 until time 1. Yeah, so this function is 0 until time 1, and then something happens at time 1. And so we can plot our function to take a look. Yep, so at time 1 you can see here we hit it with a hammer, and so it starts moving. And so remember, positive is down actually in our mass spring model, and then the mass slowly comes back. Slowly comes back to equilibrium and slows down to 0. Good. And so that's hitting it with a hammer. In fact, we could hit it with a hammer several times. What happens if I take another hammer hit at time 2 and time 3? Let's solve it again. What do you think is going to happen? Oh, you can kind of see right here, right? Inverting these, this is going to be a Heaviside at time 1, Heaviside at time 2, Heaviside at time 3. So these are kind of activating different functions here. Let's invert that time. And so here we go, Heaviside at time 1, 2, 3. And so if we plot the result, maybe I'll get time a lot longer. Oh, there we go. Oops. In fact, 10 is fine. So you can see here what's happening. I'm hitting it with a hammer, and then I hit it with a hammer, and then I hit it with a hammer. Good. Now, what happens if you hit it with a hammer going in the other direction? Oh, let's try that. This might be fun to see. Ooh, there it goes. So you can see hitting it with a hammer going in the other direction. We really knocked it for a loop there, and then hitting it with a hammer in the positive direction gave us that last hit. Of course, everything dies off because we have such a high damping factor. Let's see, where is it? Here it is. Damping factor was 3. Spring constant of 2. Okay, so that's kind of playing around a little bit with the Heaviside function and the Dirac delta function.